Thank you.
Just I had a query that how your surface topography is varying whenever you are using two or three different kinds of substrates, just like once you are using silicon, once you are using glass. So is it possible for the glass to go for such kind of thermal treatment beyond 400 degrees Celsius? Okay, so will it affect the surface topography?
At 400 degrees Celsius is not a problem to perform. Obviously, it depends on type of the glass, because
Okay,
we had some bad glass. I mean, I don't remember exactly the composition, and the glass melted at 400 degrees Celsius.
okay,
But
yes,
then,
yes, that was the issue. What I
yeah,
thought that 400 degrees Celsius, it will be quite difficult for the glass to withstand. And another question I had, what kind of difference you are observing whenever you are recording the photoluminescence for one layer and five layer? Because in five layer and one layer, what I could see from the PL spectra that there is no much difference for the bandage or the defect related emission. So is it really affecting the luminescence property?
you can see that we have here some bad. You cannot see. I
Yeah,
believe
yeah,
you
I
are
can see that.
talking
Yeah,
about
this
this
is.
this slide. Uh, Maybe a sharp slide of the energy and some defects in this region. And if we are going to see the 418, 380, 38, these defects, which we can observe them here somewhere here, are related to defects in the structure.
Yes, I can understand. But my question was that how it is differing for this one layer and five layer. That means why you are getting this kind of defect in five layer? Because for my knowledge, I can understand that in one layer you will have higher. You should have higher defect density than the five layer, because one layer is much more. One layer will have nanoparticles which are of smaller size. So smaller size nanoparticle will have higher surface to volume ratio, and hence it will have higher defects. So it was really interesting to observe higher defect concentration for this five layer uh, sample.
We didn't make this correlation because from the diffraction patterns, you can see that we calculate the crystallite dimensions, and we have 70 nanometers and 80 nanometers. So we are the range is too small to correlate the results like this.
Uh,
Okay.
okay, so as much as I hate to interrupt this scientific interaction, I need to do that for getting the talks going. So thank you so much again, Dr. Raluca, for sharing such an exciting research with us. And we should always we are taking care that our research is going into some applications, and they are ultimately giving rise to some product that is the ultimate, probably the target. And an announcement goes that if any of the researchers are having any idea which you are confident that it would lead to a product, then the SRF Foundation is glad to arrange any venture investors for the same. So please go ahead and think about the ideas, and you are free to come up with them. Thanks, Dr. Raluca, again. And
Thank you.
we will proceed with the next talk. And our next speaker is Dr. Chandrani Nath. She is a DST Inspire faculty in Special Center for Nanoscience, JNU in New Delhi. She has received her PhD in physics from Tezpur University and her particular research interest is in material properties dependent on variation of temperature and magnetic fields. And I will not take much of the time, so I'll provide the floor to Dr. Chandrani. Please go ahead.
Yeah, am I audible?
Yes, you
Yeah,
are.
so thank you so much, Dr. Sritama, for this nice introduction of mine. So I will share the slide. Let me check. Okay. I'm having some problem issues with. Am I? Are you?
No, the slide has not come up yet. Yeah, it is coming, I guess.
Don't.
Mm, but you had shared the screen, I guess.
Shall I go for a window? It's showing the same thing. Actually. Shall I disconnect and join?
Okay. Yeah.
Okay, I will just leave and join again.
So till the time Dr. Chandrani joins again, I would like to say that please keep your questions ready and you can raise your hands and ask your questions, or you can also write your questions in the chat box, and the concerned speakers would answer them eventually. So Dr. Chandrani, yeah, are you able to share it now? You are muted.
But there's no option coming here. There's your enter screen, a window, a tab. One second, one second.
We have only two left, right, Sitama?
Yes, yeah.
Okay.
Dr. Chandrani, are you there?
Am I? I'm not getting the option to share.
Saurabh, can you please help? I mean,
Can you
with the
can
sharing
you
options?
present now that upper arrow? If you click that once, your entire screen a window. You please put your entire screen, and then you go to your slide and then make it a PowerPoint presentation mode.
Just beside the hand option, you will get that option for slide for presenting your slides. Near the hand icon, please click there, and you will get the options.
Then
You are
I think
muted, Dr.
I think
Chandani.
I think we can.
No,
So
actually, I have gone, but your entire, I'll go to entire screen. Then I can't see. I can see the entire screen only if I share.
yes, you do that now.
No, you keep your PPT open. Okay,
Yeah,
you keep your PPT open.
I have kept it. Yeah.
Yeah, now it's coming.
Okay. Okay. That's okay. I'm so sorry for the delay.
Full screen mode.
Yeah, you can go to slideshow.
Yeah. So
Yeah,
can
that's great.
everyone see the slides? Okay. I'm so sorry for this delay. First of all, I'd like to thank the organizers for allowing me this opportunity to talk in this conference. So today I'll be talking about thermoelectrics, its interplay between material property and dimension. So how this material property gets affected with dimension. So thermoelectrics, this branch of study has been studied for long and having its importance both in application as well as in basic science. So basically, I will be talking about how proper choice of material and tuning its dimension can lead to better thermoelectric performance. So today's world is in serious need of energy to run the civilization. Why? Because we need energy to run industries, run automobiles, to meet the household requirements. But then there is this growing population has increased this demand, energy demand by many folds. So there comes the real concern. So what are we in then? But this increased energy demand is showing an alarming sign. Why? Because of the limited reserve of conventional fossil fuels. So this curve, as we can see, this reserve, the fossil fuel reserves that are remaining, that can only sustain another 50 years. So our future generation is in real danger. So another most alarming concern is the large emission, carbon emission that comes from this burning of these hydrocarbon fuels. So as you can see from this curve, there is an exponential rise in carbon emission, and by 2050, this will reach close to 12,000 million tons. So having a huge impact in our environment. So what does it emphasize then? So this study data emphasizes us to look for some unconventional and renewable energy sources that are clean and doesn't pollute our environment. So researchers worldwide are striving to achieve towards this goal. So what are these? Let's see. So there are certain unconventional energy sources that we get from our nature that comes from our sun in the form of solar energy, from wind, water, geothermal energy, nuclear energy, look for which unconventional and renewable energy sources that are clean and doesn't materials. So next, coming to today's topic, we'll be talking about thermoelectrics. These are materials that can that work with the phenomenon of thermoelectric effect. So what is this phenomenon then? So this phenomenon is basically direct conversion of temperature differences to electric voltage or vice versa. That means if you provided electric voltage, that can create a temperature difference. So this effect dates its discovery dates back almost 2 centuries back. So when Thomas Seebeck discovered the Seebeck effect, he actually joined two dissimilar metals, and at the junction he applied a temperature difference. So he could generate a voltage due to the temperature gradient across the junctions. So a few years later, Peltier discovered an opposite effect. He could create a temperature difference by applying a voltage across the materials across the junction. So thermoelectric materials are basically works with these two effects, Seebeck effect and the Peltier effect. So why we opt for thermoelectrics? So as I have already told earlier, that thermoelectrics provide as a renewable as well as an alternative source for clean energy. So moreover, these thermoelectrics can help us to utilize waste energy. Why waste energy? So from this diagram, we can see that most of the energy that we use, almost 66% goes out as the waste heat. That means more we use, more we waste. So these thermoelectrics can offer an alternative to recover this waste heat and use it to power other devices. Okay, so let's go about see what are the other advantages of thermoelectrics. So since these thermoelectrics doesn't emit any toxic gases, so these are very clean and it's not harmful to the environment. So these thermoelectric materials lack moving parts that reduces the maintenance cost. These are very compact to according to our need. So we can stack up our thermoelectrics to according to our need of the powering the device. So these are highly reliable. So these can be used in zero gravity environment in space also to power unmanned satellites. So these have a lifespan of more than 14 years. And another more important point here is the same material can be used for power generation as well as it can be used to cool a material. So this is a promising application of thermoelectrics. So you can see the radioisotope thermal generators. These are used for powering unmanned satellites or space probes, where usually you use a radioactive, where the heat emitted from a radioactive decay is used to power these satellites. Another important point is you can use the waste heat management from automobiles. In fact, BMW has been working this property of thermoelectric materials to utilize the waste heat to power the auxiliary features like powering the air conditioning or the power steering. So moreover, you can use these as portable car coolers. You can carry a small cooler along with you while on a drive or a picnic using these materials. So since these are a lack of moving parts and refrigerants, so these are very compact in size and it can be used for small sample cooling as well. So say it is a prototype device that can be used as wearable devices. If you have wearable devices, then that carries uses the body heat to power that device. So this has been developed by a Korean group. So that uses the body heat to power your device. So let's see how the parameters that controls this thermoelectric that gauges the efficiency of a thermoelectric material. So efficiency of a thermoelectric material is usually gauged by figure of merit. So that is described as ZT. That usually depends on the Seebeck coefficient S, electrical conductivity sigma, and the thermal conductivity kappa. So this S square sigma term is known as power factor. So for a good thermoelectric material, as you can see from this equation, a good thermoelectric material should have high S, high Seebeck coefficient, high electrical conductivity, but low thermal conductivity. So for practical applications, you need ZT should be greater than 1. So, but it's as it's said that it's better, is easier said than being done. So increasing ZT is quite challenging. So why? Because these parameters, as I described in the earlier slide, these are interrelated. Okay, how? From the Morse equation, we can see that the Seebeck coefficient is inversely proportional to conductivity. That means if we try to increase the conductivity of a material by doping, by increasing the carrier concentration, on the other hand, what will it happen? On the other hand, the Seebeck coefficient will continue to decrease. Okay, so that means we should tune our material in such a way that we have a maximum value of power factor, that is S square sigma, that comes in somewhere in between the carrier concentration. So basically, as we know, we have mainly three types of materials: metal, semiconductor, and insulator. So this table shows how the different parameters have different values of these three main materials. For metal, we have very low Seebeck coefficient and very high electrical conductivity, as well as very high thermal conductivity. But insulator, on the other hand, have very high Seebeck coefficient, but very low electrical conductivity and very low thermal conductivity as well. So what comes in between? The semiconductors. So these semiconductors are known to be the base thermoelectric materials, which are heavily doped and can have carrier concentration in the range of 10^19 to 10^21 carrier per centimeter cube. So how does this affect our figure of merit ZT? So as we have already seen, thermal power, and that is sigma S, thermal power we say S, there's a Seebeck coefficient is inversely proportional to conductivity, electrical conductivity. In terms of carrier concentration and effective mass, the relation are shown here. So from this relation, we can see that high S means high Seebeck coefficient requires large effective mass. On the other hand, if you have large effective mass, the conductivity will decrease. So again, in terms of carrier concentration, we see for high Seebeck coefficient, the carrier concentration needs to be low. But for high sigma, the carrier concentration needs to be high. So that means if we try to tune S, sigma will decrease. On the other hand, if you try to increase sigma, that is electrical conductivity, S will decrease. Right. So this tuning doesn't help us much. So there is another term in the figure of merit in the denominator. That's the kappa. There's a thermal conductivity contribution. So now this thermal conductivity has two main contributions, one coming from the electrons and another from the lattice or the phonons. So, but here again, another term sets in. This electronic contribution of thermal conductivity is determined by the electrical conductivity from the Weidmann-Franz law. That means if we increase electrical conductivity, this contribution keeps on increasing. That is, the electronic part of thermal conductivity will increase. So these contradictory requirements has hindered the progress of thermoelectrics towards achieving higher ZT. Now, how we actually increase its efficiency? So now let's just see how do we, as we have already seen, what are the drawbacks, what are the hindrances that causes the that has been not allowing us to improve ZT only by increasing either by increasing S or by increasing sigma. So what can be the possible solutions? So let us see what are the possible routes to increase the efficiency. So we can modify the thermal conductivity. There is one term that we can play with. So that is the lattice part. There's a phonon contribution part. So how can we do that? By introducing heavy metals as they're difficult to vibrate. So if we introduce heavy metals, the phonons, it will not vibrate. So what do you mean by thermal conductivity? These are just movement of phonons, that's the lattice vibrations. So if we have heavy metals, the phonon vibration will reduce. In turn, it will reduce the thermal conductivity. That is the lattice contribution of thermal conductivity. On the other hand, we can also use complex crystal structures that will also reduce the thermal conductivity phonon part. So another important point here is we can increase the percentage of interfaces and surfaces to enhance the phonon scattering. The phonon, if we increase the phonon scattering, that will hinder its movement. So in turn, it will reduce the phonon part of the thermal conductivity. On the other hand, we can also modify the Seebeck coefficient S by tuning the DOS, that is the density of states. Why? Because the slope of the density of states is related to thermal power, that is S. This is Seebeck coefficient. So now this tuning, how can we do? This tuning can be done by nanostructuring. So herein comes the nanotechnology. Herein sets in nanotechnology. How? So let us see how nanotechnology helps us in increasing the efficiency of these thermoelectrics. So enhanced phonon scattering at interfaces or surfaces of nanomaterials due to increased surface to volume ratio. We all know that as we go from bulk to nano, we have more surface to volume ratio. That will increase the surfaces or interfaces, and in turn it will affect the phonons movement. So it will reduce the lattice part of thermal conductivity. On the other hand, we know as we go from 3D to 1D or 2D, as we go below from bulk to nano dimensions, it will effectively change the density of states, its shape. So increasing the slope, which will effectively increase the Seebeck coefficient. So here in this curve, we can see how nanostructuring have increased the ZT considerably from 1 to close to 1.4 for bismuth antimony telluride. So let us see, there are several families of thermoelectric materials. Mainly there are oxide-based materials with layer structures, the Hostler alloys that operate at quite high temperature, 900 Kelvin. These are Scudder's material, topological insulators, and clathrates as well. So I will not go in detail in this. The structure of these materials will move towards our topic of discussion. So my main interest is in oxides as thermoelectrics. Why? Because these oxides have high operating temperature. These are very easy synthesis method. These are material availability is very easy. So these materials are formed by ionic bond that helps us to play with its chemical composition. So its high electronic correlation gives a high effective mass, as which in turn is helpful to get high Seebeck coefficient and hence high value of ZT. So ZT is reasonably high, close to 1 at 1000 degree Kelvin. So, as I have already told in the beginning, not only as application, thermoelectrics is also very much important as basic science. So it helps us to know the mechanism that is included in the carrier transport, as well as it helps us to know what type of carriers are contributing toward this Seebeck or the thermoelectric property. So similar to Hall effect, as we all know, Hall effect gives us the nature. We know the nature of carriers from Hall effect, either it's a hole or an electron. In a similar way, the sign of Seebeck coefficient lets us know which type of carrier is involved in the transport. Right? If we have positive, as that is positive value of Seebeck coefficient, then we know that holes are the carriers in that material. And if the Seebeck coefficient is negative, we know electrons are the main carriers in that type of material. So this coming to my study, I have studied hybrid system with strontium titanate as oxide and with graphene. So my main idea, since strontium titanate has a very low conductivity, close to 10⁻⁻⁶ Siemens per centimeter. So my idea was to improve its electrical conductivity, as well as since I'm using as a filler, graphene as a filler in it, as well as to decrease the phonon, phonon part of the thermal conductivity. So this is a typical, we could synthesize nanoparticles of strontium titanate with a average particle size of 42 nanometer. So this is the same micrographs of hybrids. This is the plain strontium titanate. This is the image of the hybrid. This we can see graphene nanoflakes here. So we have done the routine characterization of XRD and XPS we have done. So in XPS, we have found that with increasing the loading of graphene, there was a shift in the SR3D peak that was mainly due to the amorphization of strontium titanate, because more graphene loading was providing a strain in the SRO bond. So let's move to our main study. So from the electrical conductivity plots, there's a resistivity versus temperature plots. What we could identify, we had modeled this mechanism by the heterogeneous model. So what we have found that in graphene, the movement of electrons takes place in between in the graphene nanoflakes, as well as the conduction of electrons takes place from one graphene to another, hops from one graphene to another graphene flake. So what we have modeled using this heterogeneous model, where he suggests that in the graphene nanoflakes, the metal conduction was mainly occurring as metallic conduction. As we all know, graphene is a very good conductor. On the other hand, tunneling of electrons were taking place from one graphene flake to another graphene flake. So let's move to our thermopower graph. So here, we got one interesting result here. So strontium titanate by nature is N-type, with S close to minus 380 microvolt per Kelvin. But what we found interesting is that our nanohybrids were P-type. Here we found that our thermopower value is positive, concluding, giving us a conclusion that our nanohybrids has turned from N-type to P-type semiconductor. Why? So we have given a plausible assumption to it, since graphene is a very good electron acceptor. So the electrons from strontium titanate move to graphene nanoflakes and in all turning the whole system into P-type. Next, let us move into the thermal conductivity and ZT plots. So as I have already told, we have included graphene as a nanofiller so that to increase the phonoscattering. So we have tried to decrease. We have been successful to decrease the thermal conductivity. Here, as you can see, for strontium titanate, usually the value of thermal conductivity is 10 to 12 watt per meter Kelvin at room temperature, while for graphene is all know graphene is a very good thermal conductor as well as a very good electrical conductor. So for graphene is close to 4000 watt per meter Kelvin. But for our system, we could considerably decrease the kappa value to 0.83 to 3.03. This value depends on the loading of graphene at room temperature. But we are very unfortunate to get a very low ZT value. So these methods, of course, this doesn't have much place for practical application, but we could actually develop P-type. This P-type nature of this nanohybrids is very much interesting. So let's move to our move to a different system that have worked, although this work is still going on. So what I have done, V2O5 has a very good value of Seebeck coefficient. So we tried to increase, but it has a very low value of electrical conductivity. So we have tried to increase its electrical conductivity by more or less retaining its good value of Seebeck coefficient by doping it with ruthenium. So these are we could typically synthesize its nanoparticles with various concentration by of ruthenium. So this is a practical graphs of temperature dependence of conductivity and Seebeck coefficient. Here also we have got some very interesting results. So what happens here for V2O5 has typical conductivity value at room temperature is -4 Siemens per centimeter. But for ruthenium doped V2O5, we could successfully increase its sigma value close to 5 Siemens per centimeter for the highest concentration of ruthenium, that is 20%. But here again, there is a very interesting observation with S, this thermal power. For V2O5, thermal power is usually negative, that is minus 250 microvolt per Kelvin. That means here electrons are, as I've already said, the sign lets us know what type of carriers are taking place in the conduction mechanism. So here we know this is an n-type semiconductor. So, but in case of this of ruthenium doped V2O5 system, what is happening? There is a change in the thermal power value with temperature. So it's usually what happening, as there is a crossover from positive type to negative type. So this interesting result is I'm yet still studying what is the nature, not yet have come into proper conclusion, the nature, but there's this interesting result is very much important here, and we could successfully but then, as I've already told, that if you increase the carrier concentration to increase the electrical conductivity, S will considerably reduce. So this is what's happening here. The value as for undoped V2O5 S is about 250 microvolt per Kelvin, but as we are increasing the doping, the S value is also decreasing. So this for 5% is 137 microvolt. This decreased to 137 microvolt per Kelvin. For 20%, its its values is close to 6 microvolt per Kelvin. So here again we are showing here the thermal conductivity value. So it's very interesting here to note that for ruthenium doped V2O5, we could successfully reduce its thermal conductivity to 1.9 watt per meter Kelvin at room temperature. And we have got this ZT value of 0.10 to the minus 2, close to 10 to the minus 2, close to room temperature here. So this result is very interesting, and if we go into deeper study of this might have some practical application. If you try to tune these dopants as well as its size to increase its practical application. So how much time do I have left? Hello?
You have about 5 minutes more.
Okay, so I will just quickly go about these polymers. These have very important results and it's very interesting. So, so polymers, as we know, these are some insulating materials that actually help us to insulate conduction. But this special type of conducting polymers is a conducting polymer that also conduct, as well as they have this flexible nature. So as I've already said earlier, that ZT needs low thermal conductivity. So these polymers are very much interesting. Why? Because these polymers can be tuned. So this usually comes in the semiconductor range. So, and since these have intrinsically low thermal conductivity, these polymers can have important implications as possible thermoelectric materials. So so what we have done, so we have actually synthesized a polyaniline and CSA doped nanotubes. So I'll quickly go into the results. So what we have found here, that the S value is very high, close to at the low temperatures, close to 0.6 volt per Kelvin. Right. So so this high value of, and this peak is actually due to the phonon drag effect. So I'll not go into detail what is this. So I'll just want you to know to the go to the results. So here, as you can see, this is a ZT value. So we have got 0.77 at 50 Kelvin. This is quite at low temperature. So this particular material can have application for low temperature cooling for quantum computers, or if we go for cooling or recovering the waste heat for devices that operates at low temperatures. So that's all, I think. If I think I have completed on time.
Yes, you're quite on time, Dr. Chandrani. Thank you so much for taking us through the interesting aspects of thermoelectric materials and your exciting research. I would just spend few seconds to check if somebody has any questions on this. Any questions, please? Okay, so if there are no questions, then I would like to thank again Dr. Chandrani for your nice talk, and we will proceed with the last speaker of today's session, um, Dr. Anshuman Rai Chaudhuri, uh, who is research scientist now in the National University of Singapore. And before that, he was my senior. We worked together in Professor Pradeep's lab in IIT Madras, so I know him from there. He obtained his PhD from IIT Dhanbad, and his main research interest is on synthesis of various nanomaterials for diverse applications like sensing, drug delivery, catalysis, etc. So uh, I would like to request Dr. Anshuman to take the floor ahead.
Yes, am I audible?
Yes, you are.
Yeah, thank you, Dr. Sitoma, for the nice introduction for mine. And thank you to all Science Dialectica team for inviting me. I am very happy to share my research in this type of platform. And I'm seeing the Science Dialectica from its born, right? I'm very happy to see the growth of the Science Dialectica in the meantime. So today, what we will do, and especially for the invitation, I am thank you to my dear senior, Dr. Saurabh Kantijana. So,
So,
so what?
sorry to interrupt you. You do that presentation mode. That
Yeah, now it is okay.
is,
Now it is okay.
No, it has not come yet as a slideshow.
you do one more time. Maybe
Okay,
similar.
then I am doing stop sharing, and again I am resharing it.
Let's do. That's better.
Now it is fine. Now it is.
It is still not in the
You please just
slideshow
hold.
mode, I guess.
Anshuman, you just please hold for a while.
Okay.
Who is ML? Please mute your video.
My video, right?
Is you? No, not your. Somebody is joined. I removed him, but I don't know who is. It is showing that ML. Please remove. Please turn off your video. Otherwise, I will remove you. Sorry. Anshuman, you carry on.
Yes, yes. So, Saurabh, actually, I am trying to. Now it is visible.
It is coming. You do once more.
And now the slide is visible to you.
Slide is visible, but not that in
Full screen mode, no. So now it is full screen.
No.
No.
Oh,
One thing you can do, you can screen share.
Screen share, right? Screen share. Okay,
is,
I am doing that. I am doing that. Show your entire screen, right? Share. Now it is okay.
Yeah, it is coming, I suppose. You go to that your presentation.
Yeah, now.
Yes. Now you full screen mode.
Yes.
Yes. Perfect.
Yes. Thank you. Thank you very much, and I'm sorry for the time delay. So today what we will discuss, today the chemistry in micro droplet. So actually we know the various synthesis approach for the synthesis of just a minute, for the synthesis of nanomaterials, especially solvothermal synthesis, hydrothermal synthesis, wet chemical synthesis, sonochemical synthesis, and many more. So many syntheses we have the usual synthesis we know. Today we will discuss some unusual synthesis method for the synthesis of the materials. And for that, what we will do, we will take some ions, metal ions here. That means the precursor in capillary tube, it will be a glass capillary, and we will put a metal wire just like a platinum wire into it, and we will give some potential to the platinum wire electrode, and eventually the solution will be coming through that capillary, and this from here as some droplets. So we will show that we will call that this is spray will be happening. It will some spray plume will be generated. It will be coming through some droplets, and these droplets will be behaving just like a tiny reaction vessel. That means the reaction will be happening inside that tiny micro droplet. Sometimes we will call as a droplet in general. So the materials will be synthesized inside that tiny droplets. That's why we are termed as chemistry in micro droplets. So this is a new approach for the synthesis of the materials. So now coming to a paper that was published in 2014. So from what they have done, they have taken silver ions inside the droplet, as I told you before, inside the capillary, glass capillary, and they have gave some potential to that through a platinum wire electrode. The ions are coming out through that capillary, the nozzle of the capillary, by some micro droplet, and when it is deposited to a substrate, then the ions, that means silver plus, will be getting electrons from the substrate, and it is reduced, and it produces this type of nanoparticles. You can see here the nanoparticles are formed. So this is so silver nanoparticles are formed, and these nanoparticles are formed, means there is no need for any what is called, that is workup or all, because only the ions we are giving, there is no reducing agent are using, no other chemicals are used, only silver ions in water, and we are spraying, we are giving some potential to that. The droplets are formed, and that droplets are reducing when it is falling on the substrate, getting electrons from the substrate. So Ag plus will get some electron, and it will form Ag0 for the producing some nanoparticles. So this was after that, what we have done, we have taken not only the ions, we have taken the polydisperse nanoparticles inside the capillary. This is the capillary, the glass capillary. Inside that, we have taken the polydispersed silver nanoparticles, and we have sprayed the similar way. That means we are giving some positive potential through the platinum wire electrode, and the polydispersed nanoparticles are coming through the droplets. As you are seeing here, the micro droplets are forming charge, although we can call that charged micro droplets are forming. The positively charged micro droplets are deposited to the substrate. This is negatively charged, and these droplets are positively charged. And when it is deposited, I told you, it will get electron and it will reduce. So what is happening here? These charged micro droplets are producing are transforming the polydispersed nanoparticle to a uniform assembly of monodispersed nanoparticles, as you are seeing here. So this droplet induced process is happening within a fraction of a second. That is the beauty of this type of synthesis. This is happening within a microsecond time scale. Usually this phenomena is called electrospray. Spray is happening by using some potential. That's why it is electrospray, and this electrospray is happening within a microsecond time scale, and polydispersed nanoparticles are forming the monodispersed one within this type of time scale. So that is the main advantage of this process. So what we have done, AgNO3 silver nitrate and phenyl ethanethiol we have taken, and sodium borohydride we put that, just the normal synthesis, it is a reducing agent, and the silver nanoparticles are formed. You know, for the usual synthesis, the disadvantage is that there is a possibility of the polydispersed nanoparticles, and there is no use of the polydispersed nanoparticle for the any applications. If you go for some sensing or some other industrial applications, always people are asking for the monodispersed nanoparticles. And for monodispersed, from the means post synthetic modification of the polydispersed to monodispersed, there is also, although there is a process that is called digestive ripening. You know that that is the old process. So digestive ripening is the process. For doing the digestive ripening, you have to give some digestive ripening agent. That means some chemicals you have to use. You have to give some temperature. Sometimes you have to play with the pH of the solvent. Some more acidity or basicity will be needed for the conversion of the polydispersed nanoparticle to monodispersed one. So we are producing the monodispersed, the uniform assembly of nanocrystals by the ambient electrospray, and we term this process as ambient microdroplet annealing. Ambient microdroplet annealing is a newborn means approach for the transformation of the polydispersed nanoparticle to the monodispersed one. So now, so this is the before spray, as you have seen. Again, I am telling you, this is the before spray and this is after spray. And here you can see how monodispersed it is. One particle is, there is a hexagonal arrangement of the nanoparticle crystal is forming. So sometimes we are calling this as superlatives of the nanocrystals. So this is the after the spray, you can see the electrospray of the polydispersed silver PET nanoparticles at optimized condition. You know, again, I am going to the previous slide. For getting this type of particles, we have to play with some different parameters. What is that? First is the tip to collector distance. That is very important. Tip to collector. The tip of the tip of the glass capillary from where the microdroplets are generating, and the collector, that means the substrate where the material will be gathered. So this distance, because if the tip to collector distance is more, then the droplet size will be different. If it is less, then the droplet size will be different. The droplet size will be the other one. Another one is the potential we are applying. So potential, we have to play with the potential what we are giving to the platinum wire electrode, tip to collector distance. Again, the solvent of where the material is dissolved. So that is also a parameter. So when we have optimized all the conditions in each cases, so then we are at optimized condition, means conditions, we are getting this type of structure. This is, you can see the when you are, this is for this type of particles, there is a the particle size distribution is very high. So there is a 2 nanometer of particles are also there, 25, 30 nanometers of particles are also there. So the particle size distribution is more. And here, after the spray, you can see there is a means particle size distribution is very less. So we are getting uniform distributed particles. And the even more important thing is that the particle distance is also uniform for all of the cases. It is 1.2 nanometer we measured. So and this is the PET we are using, the phenyl ethanethiol, the size of the phenyl ethanethiol molecule is 0.7 nanometer. It is observed. And when this nanoparticle is also protected by phenyl ethanethiol, this one is also phenyl ethanethiol. So there will be two phenyl ethanethiol will be there, and they are interdigitated. So when they are interdigitated, it will form 1.2 nanometer distance. That point I want to tell you, when the ligand will be different, then the particle size, if the ligand is more, if we are using some polymer kind of materials, then the particle distance will be also it will increase. And if we use some other means ligand, then the particle distance will be less, but the film will be also more compacted. After the after spray, we have also characterized the material throughout. We are using some UV visible and XPS and TM we have done, and we have seen that the particle what it is producing, it is also a silver nanoparticle. So there is no impurities. It is not silver oxide. So silver nanoparticle is producing again silver nanoparticles. So Next, so I previously I told you we have to optimize some parameters. So effect of distance, tip to collector distance. If we means previously I told you if the tip to collector distance is more, then there will be means so again suppose here it is A is when the tip to collector distance is, just a minute, when it is so A is 0.5 centimeter tip to collector distance. This is 1.52, like that way we are increasing, and this one is 4 centimeter tip to collector distance. So when the tip to collector distance is less, that means there is a very less time to reorganize the particles. I don't know. So suppose if it is less, so then the particle or the droplet will achieve very less time to reorganize. That's why the reorganization is not happening. You can see here also the monodispersity is arising. Here is less monodispersity. You can see the particle size distribution, it is more. Here it is less, but the assembly is not there because of the particles are not, means the droplets are not getting much time to reorganize or reassembly the all of the things. When it is 1.5 centimeter tip to collector distance, it is getting a perfect conditions to reorganize the particles and form the superlative structure. Even if it is more, then maybe the the droplets are evaporating, and when the droplets are evaporating, it is not getting the perfect environment to form the this type of assembly and all. Next, so is it moving? Am I audible?
Yes, you are audible. Yeah, something. I think it is stuck somehow.
Oh, so this is slide number 3, right? 5.
Yes.
This is slide number 5. So I don't know. Yeah. Now the applied. Now it is 6, right?
Yes.
Yeah.
Yes.
So if it is, now we are coming to voltage. So the voltage is also playing a crucial role for getting this type of particles, right? So when the we are playing with the voltage, this is 0.5 kilovolt, 1.0, 2, 3, 5, and 7.0. Like that way we are. So when the voltage is 5.0, we observe that the perfect superlative structure is observing. When it is more, so then there is not the superlative, the monodispersity is, although it is arising, but the perfect monodispersity assembly is not achieved. Now coming to the flow rate. So when the flow rate is also a crucial thing, because when it is regulating the droplet size. When the flow rate is more, the droplet size will be less. When it is flow rate is less, the droplet size will be more. So when the droplet size will be changing, then the particle size will also be changing. So when we observe that when the flow rate is 1.0 ml per hour, we are getting such kind of assembly. Now coming to the solvent. Solvent means where the material is dissolved. The solvent solvent is giving a different pH in the microdroplet environment. It is giving a different dielectric constant to that, and also in a different solvent, the material's dissolved property will be also changing. So when we have arranged here the solvents in a particular dielectric constant. So we have started with carbon tetrachloride. It is the dielectric constant is 2.4, and we are going to the acetonitrile, that is 38.25. So we've seen that when in a particular range of dielectric constant, suppose it is the chloroform is 4.41. From here you can see here there is no monodispersity is achieved. This is polydispersed particles, means even more, and this is also polydispersed. But when it is dielectric constant is around 4, then the monodispersity is started to form. And 7.82, that is tetrahydrofuran, the monodispersity is there, means, but the assembly is not there. But when in case of the dichloromethane, when it is the dielectric constant is around 8, the superlative structure is forming. So like that we have also optimized the solvent for the electrospray. Now coming to the so when we have spraying these things in a different liquid. So this is means in spite of giving one nozzle spray, we have used here 3 nozzle spray. to get more assembly of the particles. So we have sprayed in the similar fashions on different means liquid. So we have seen that when we have sprayed these things in water, we are getting this type of perfect superlative structure. We term these things as nanoparticle nanosheet. Nanoparticle nanosheet means the nanosheet is formed by the assembly of the nanoparticles. So you can see when the particles are deposited on the water, so then the particle size is around 4 nanometer, and the uniform distribution of particles are there. And this is the optical image of the film. So it's a quite large film is observed, and this type of film can be used. This type of thin film can be used for some fluorescence applications, sometimes the conductivity measurements and all. And although also the particles when it is deposited on water, the perfect means crystal of the silver is obtained. So after that we have started spray more for the more time, and we observe that when the spray is more, then the layer upon layer deposition is happening. That is more interesting thing. So when the layer upon layer deposition will be there, then there is a possibility of formation of the 3D crystals. So previously we got the 2D assembly of the materials, 2D crystals we have obtained, and if we are spray more and more, then the droplet upon droplet deposition will be there, and there is a possibility of formation of 3D crystals. And we can use this type of electrospray as a 3D printer. So we can generate a 3D crystal of different metals, and can be applied for many versatile applications. So although the mechanism, we will just discuss here the phenomena, and because the mechanism, if the proper formation mechanism of such type of assembly and the materials are still unclear. So possible mechanism what we have observed. Before that, before going to the mechanism, I am telling you that this is when we have I told you that is electrospray, because we are giving some potential for generation of the droplets. Without giving the potential, also we can give some nebulizer gas to generate the spray aerosol. The droplets are basically aerosol. So from the generation of the aerosol, we can give some nebulizer gas for getting this type of aerosols, and these nebulizer gas are also producing the monodispersity of the structures, but the assembly is not there. For what? Because when we are giving the nebulizer gas flow, the gas pressure is there. So if the pressure, so as the pressure is there on the substrate, so the particles are moving around. That means there is no scope for getting the assembly of the particles, but the monodispersity is achieving. So we can't say that only electrospray is producing or the voltage is giving the voltage is breaking the nanoparticles and forming this. So that I wanted to tell you, the voltage is not the case for the breaking of the particles. The particles are breaking inside the droplet, because inside the droplets there is a Coulombic repulsion forces is there, Laplace pressure is there, and so many cases, so many factors are affecting inside the charged microdroplets. Still that is unclear. So this is producing such type of assembly. And when we are going to the to find the possible mechanism, we observe that we hypothesize that the silver, what we have done, we are producing silver, we are giving silver phenylethanethiol, and we are reducing this by sodium borohydride, and the nanoparticles are formed. When the nanoparticle is sprayed, these nanoparticles are again producing some silver thiolates, because we know that the nanoparticles and the clusters are also decomposing in presence of light or other exposure. So like this one, the materials are producing silver thiolates inside the droplet, and these silver thiolates means there is silver ion and thiolate, Ag plus and thiolate will be there. And these silver thiolates, when they are depositing, they are getting electron from the substrate and producing silver nanoparticles. So like that way, the monodispersed particles are forming. Means the polydispersed particles are producing transient precursor species as silver thiolates, and they are again reorganizing to form the monodispersed particles. Because here also for the control experiments, we have taken silver thiolates and 3 different tip to collector distance we have sprayed, and we have seen that the 0.75 centimeter distance, the perfect superlative structure is arising. Now, so till now I have discussed about the silver, the phenylethyl thiol protected silver nanoparticle. After that, we have checked these things with the ethane thiol protected silver nanoparticles, and we have started spraying. So for the silver ethane thiol protected silver particles, this is before spray and that is after spray. So what we have seen for what we optimize the parameters for the phenylethyl thiol, that is not working with the ethane thiol. So for the ethane thiol, to getting the monodisperse particle, we have to play with the conditions, and we observe that when the voltage is 4 kV and the tip to collector distance is 1.0 centimeter, then it is producing silver monodisperse silver particles. Now we are coming to the dimethyl benzene thiol protected silver nanoparticles. So as synthesized particles are all, we know that this is the polydispersed nanoparticles, as most of the cases the silver producing polydispersed particles, and we have started spraying that, and we found that the optimized condition for getting the monodispersed particles where the particle size distribution is below 5 is where the voltage is 8.5 kV and the tip to collector distance is 1.5. So that I wanted to say you, for different particles, the optimized condition is different, but it is possible to get the monodispersed particles. So that's why we can say that is a generic method. The electrospray can be used for the conversion, for the transformation of the polydispersed particles to monodispersed one. We have patented, we have filed this patent, and recently it is granted. Now coming to the, so we will discuss with the another another particle morphology. So what, this is the paper published from our senior, that is Dipanjan Sarkar. So in it is published in 2016. What they have done, they have the similar way they have sprayed the silver acetate on the substrate, and it is producing a bush kind of structure. One dimensional bush is forming. That is very interesting. So what is there? So when they have spray, as I told you before, the platinum wire electrode is there, and silver acetate they have taken in water, and they have started spraying on a TEM grid, because you know TEM grid is a metal substrate. On that the spray will be very nice. So if a particle upon particle one particle is formed, again suppose when the droplets are filled with the ions, when it is deposited to the substrate, then it is producing nanoparticles, as I told you before. Then the particle upon particle orientation is happening. When the spray is, when at the beginning this type of assembly will form. When this time will be more, then this type of bristle kind of structure is observed. When they have sprayed it more time, then the nano brush kind of structure is happening, and they term these things as a necklace. The pearl necklace kind of structure is observed, and a beautiful nano bush kind of structure is obtained. And this nano bushes have applied for the many applications that I will come to you later. So previously they have sprayed these things in copper grid. After that, they have sprayed these things in many other substrates, just like stainless steel, wire mesh, copper mesh, and again on a carbon electrode. On that, different cases, the morphology of the when the substrate is different, then the morphology is little bit different, that they have observed. So they have used these meshes for the Escherichia coli bacteria trap or some particular matter capture. So they have used these materials for that. So what is the most important thing is that the bimetallic structure is also possible. So previously they have observed that is silver acetate they have sprayed on the metal substrate, and they have got a bush kind of structure for the silver. After that, they have started spraying silver and palladium together, and they have got a bimetallic and the alloy kind of structure, kind of nano brushes. So again, we are coming to another paper where the Vishwajit Mondal is the first author, who is also hearing this today's lecture. So what they have done, what is done here, that is you can see here the drilling of MOS2 nanosheets by ambient ions. That means they have the drilling of the MOS2 sheet is indeed possible by these ambient ions. So they have taken MOS2 sheet on a water. In a beaker, they have put some MOS2 sheets, and they have started spraying Ag ions. Suppose Ag nitrate or Ag acetate, they have started spraying. The beautiful thing is that there is a beautiful means piece of work. So when they have started spraying the silver ions on the MOS2 means surface, then the silver ions is reacted with the sulfur, and it will produce a silver means and silver sulfide nanoparticles, Ag2S nanoparticles is producing, and it is dissolving to the substrate, to the means water, and a holy MOS2 is formed. So I forget to mention, Dr. Saurabh Kanti Jana is also a author of this paper. So this type of holy structure, holy sheet is forming. So here some defect is observing. So what I wanted to tell you, silver ions, they are sprayed, and they on a MOS2 substrate, silver ion is reacted with sulfur. Ag2S nanoparticles are formed, and that Ag2S nanoparticles are dissolving to the water and producing a holy MOS2 kind of structure. So in other words, we can say that this electrospray can be used as a etching method for many semiconductor industries and all. So this is the characterization of the MOS2 sheets after spray. So you can say here that the holes are obtained. So beautiful holes are producing when it is, and some molybdenum rich material is obtained, and that molybdenum rich materials is producing very interesting things. They are producing some reactive oxygen species in water, and that can be used for some bacteria inactivation or the purification of water applications. So now coming to the another work. So this here I am wanted to show you the potential of this electrospray or the ambient electrospray in various applications. So so we have seen that the carbon onions are producing from the nanodiamonds by electrospray. Here it is some silicon nanoparticles are producing from when it is the silicon precursor is started spraying. It is producing some silicon. You know, silicon synthesis of silicon quantum dot is highly challenging right now. It's producing, it is getting some. It needs some more high temperature and high pressure. Some sophisticated instruments are also needed for that. So this simple method can indeed can producing some silicon quantum dots, and as the quantum clusters are also producing are also produced by the ambient electrospray. So ambient electrospray is producing some means BSA or means different ligand protected metal nanoclusters. And recently we have seen that when we are spraying MOS2 or WS2 nanosheets, it is producing a MOS2 or WS2 quantum dot. That is a very interesting one. So that what is happening when we are spraying graphene oxide? It is producing graphene quantum dot by electrospray within a fraction of a second. So a zero-dimensional material is forming from the transforming from the two-dimensional nanomaterials. So here I want to ask you one question, that is, if the bimetallic nanoparticle or trimetallic nanoparticle is possible by using some by this electrospray, then is it possible to get some high entropy alloy by this electrospray or not? So if we spray the gold, silver, copper on and palladium or some, what is high entropy alloy? High entropy alloy is when the alloy where the more than 5 elements are there. So this so more than 5 elements are, when it is properly mixed, it is called high entropy alloy. So then suppose a alloy where gold, silver, copper, nickel, palladium, or sometimes platinum, this type of metals are there, it is called high entropy alloy. So for the carbothermal shock synthesis are right now it is usually used for the synthesis of high entropy alloy nanoparticles. Carbothermal shock synthesis is high energy is needed for that. High temperature and high pressure is needed for getting the high entropy alloy. So if we use this, we can try that this type of simple synthesis method can be used for the synthesis of the high entropy alloy or not. And high entropy alloy and even more, the development of 3D crystals or nanoparticle assemblies of solid is possible or not. So for that we have to optimize maybe the same parameters, that is tip to collector distance. Sometimes it is applied voltage, concentration of the precursor, and the effect of pH and the solvents we have to check again. So with the collaboration of Dr. Saurabh Kanti Jana, one work is happening, that is that is also very interesting work. That is we are spraying the silver and gold on interdigitated electrode in the similar fashion. So you know what is interdigitated electrode, where the two electrode is interdigitated between that, and the gap of the interdigitated gap is very less here, that is 5 micron. So we are spraying a setup we have generated in our lab. So very cheap, we by our own this setup is created. So this is the spray tip, and the voltage is giving by that. And this means here the capillary is there. So in the capillary, the gold and silver salts ions are there, and this whole setup is incorporated in a plastic box, because then we can means easily neglect the ambient atmosphere, means the moisture and all. So we are spraying inside the box, and so there means and also we are keeping the interdigitated electrode inside the box, and the spray is happening on that. And after that, in this region we are spraying, and there is two pad, that is from there we are connecting the means our two means probe, and getting the means what is called, that is we are measuring the resistance in x-axis, and means resistance versus temperature we are plotting. And here you can say that the resistance versus temperature plot, and we are expecting if it is possible or get some means high conductivity, high temperature superconductivity is possible for gate or not. We are checking in different materials. So now this process is why this process is important. So this is no solvent is using. That means there is no use of the harmful chemicals or the organic solvents we are not using. The proper this synthesis is happening in a particular one solvent only. Sometimes it is water, sometimes it is a means cheap organic solvent like DCM and all. There is no workup is needed. The workup is generally used to neglect the impurities. That is a very crucial step for getting a pure nanocrystals. So no workup is needed. As synthesized materials can be characterized or applied. So because there is no impurities, there is no impurity is there, no muck will be there, because the spray is only the ions are is depositing on the substrate for getting the materials. This phenomenon, this process is fast. This process is ultra fast. That means a million times faster than the usual process. The phenomena is happening in room temperature. That's why it is ambient process. Limited equipment is needed. We can easily set up these things in our home also. And this is the direct analysis is possible because we are directly sprayed on the TEM grid and go for the analysis. We can directly spray on the metal substrate and go for XPS analysis. So direct analysis is possible. So now the question is that, is this scalable? We have to work on that, and means complicated reactions is possible or not. So that we have to check. So that will be our future prospect, future scope of this work. So I am so this work is happening on Professor T. Pradeep's groups. This phenomena and this science is developed by Professor Graham Cooks and Professor T. Pradeep. He is the supervisor of Professor T. Pradeep. He is a postdoctoral supervisor, and these two means here and this work is happened in Professor T. Pradeep research group, many with the collaboration of the many other peoples. I think Saurabh is here, and so I'm thankful to all the people. Vishwajit is here.
I am also there.
Yeah. You are also here. Yeah, exactly. So I'm thankful to all, and thank you to all for the kind attention. Thank you.
Thank you, Amshumanda, for a very nice and extensive presentation. You talked about a very beautiful as well as emerging research field. So we are now kind of overshooting the time by about half an hour, but we have one question from Dr. Shayan. Can we take it quickly, Dr. Shayan?
Yeah, thank you. It was a very nice talk, a very good work. Okay, so Dr. Anshuman, I had a query that you talked about that that nanostructures which has a high entropy. That means it's a mixture of different metals, 4 or 5 metals. So
Yeah.
my question is that whenever you are mixing so many species, so is there any probability that the resistance in such metallic nanostructures will go high? That means I had the confusion whether the scattering event will be more in such kind of material where you'll have multi-grain structure. That means different
No,
species will have different grains, so the scattering will be also high.
yeah, that is true. That is true. That is a very interesting question. So what we will do, we will successively we will add the metal. First, the monometallic nanomaterial will form, then bimetallic. So bimetallic plus monometallic, then trimetallic. Trimetallic plus monometallic, then tetrametallic. Like that way, we have to proceed by this approach. What I am thinking.
Okay, that means this has not been done completely.
No. That is, I'm there. We are planning to work on that.
Okay. That will be a very interesting topic, because
Yes,
whenever you have whenever large number of grains of different species, so how
yes,
this electron transport is occurring in such
true.
nanostructure, it will be quite interesting to see. Thank you.
Yes. Yeah. Thank you very much.
Thank you, Dr. Anshuman, once again. And I
Thank you
would
so much.
like to mention that please don't leave the meeting this soon, because we are having a photo shoot at the end of today's session. So we had a very nice series of presentations by eminent scholars and scientists from India and abroad. And and I would like to present a short summary of what we heard today. So the session started with Mr. Abir Chakravarti, who talked about the importance of interdisciplinary science, and he shared various aspects from his valuable experience throughout his work life. Then we went with Dr. Mahendro's presentation on artificial intelligence, which talked about the theory of intelligence, and talked about its basics, the analytic, creative, and practical type constituents and categories of intelligence. And he also told us about the past, present, and future of artificial intelligence, the problem and their solutions. Then proceeding ahead with Dr. Raluca, who presented her work on thin films. Her research is on low-cost water-based chemical solution deposition, and and the materials that she had made with sputtering and physical deposition, and their optical and electrical property studies. Then came the presentation by Dr. Chandrani, who talked about thermoelectric materials, their properties and dependence on dimension, her research on metal oxide graphene nanohybrids, doping and polymers in thermoelectric field. And lastly, Dr. Anshuman talked about using microdroplets for material synthesis, process optimization, their characterization, and various case studies and potential of high entropy alloys. So this was to summarize today's talks, and I would like to welcome and also invite all the attendees again for tomorrow's session, which is essentially going to start in the morning from 10 a.m. IST, and the session 2 is going to start from 3 p.m. again, and we are having some notable speakers with some interesting talks tomorrow. For example, Professor Abhishek Chaudhary from Aizer Mohali, and Professor Arup Kumar Das from IIT Roorkee. So let's not miss these interesting talks, and we shall be present tomorrow again at the same place. So yeah, so now, so if all are there, then let's just switch on our videos and have a photography session. Saurabh?
Please turn on your video.